Hello student, welcome to the Web Optics course. Today we have lecture number 39 and in this lecture we are going to discuss about the grating spectra that we have discussed in the last class. We continue this discussion. So, this is lecture number 39 and we are going to discuss grating spectra. Before going to the grating spectra discussion, let me remind what you have done so far. So, first we discuss about the single slit problem. Let me draw the physical structure of the single slit. And we have here a slit. So, this is single slit, and for that we have intensity distribution expansion, and intensity distribution was this. Then this is 1. Then we had double slit, an aperture like this. Instead of having one window, now we have two windows placed side by side. So, this is double slit, and for this we had the expression of intensity at some point in the screen is this. And finally, for grating we have multiple slits. So, not only one aperture, we have this multiple tiny apertures. Multiple number of slits are there. Okay. For this we calculate I theta. The most general form that one can have is this. We have sine square beta divided by beta square, then sine square n alpha divided by sine square alpha. So, in the first case it is, this term is totally due to diffraction. So, this term is totally due to diffraction. Second case, this term is due to diffraction and this term is due to interference. This case, this term is due to diffraction, and this term is due to interference. Here alpha is k by 2 a sin theta, and beta was k by 2 b sin theta. What is a and b, that we also defined. So if I draw a slit, for example 2 slits, this is a structure. So the separation between the 2 slits is A, and width of a single slit is B. That was our definition, and based on the definition we calculate everything. So that is the overall structure we have. That is the thing we calculated so far. Now we try to understand the spectra of these, these grating for the grating structure. So we already had this spectral distribution, that is coming due to the sine square n alpha divided by sine square alpha term that we discuss. So we have a principal maxima, and then we have some secondary maxima and also some minima. So these are the spectra, and this is due to the function sine square n alpha divided by sine square alpha. So these are the maxima. How many maxima and how many minima we have, we can calculate. This is 1, 2, 3, 4, 5, 6. So we have 6 minima here. If we have 6 minima, then the number of slits n is 7, and we have, if it is, then the number of maxima should be 5. So here we have 1, 2, 3, 4 and 5. That is the number of secondary maxima in between two principal maxima, and that is the condition we have. And also we calculate what is the ratio between these and these. If this is intensity, peak intensity is of the principal maxima, and if the intensity here is say secondary maxima, then the ratio we calculated in the last class, and that is I secondary maxima divided by I principal maxima PM. That quantity is 1 divided by 1 plus n square minus 1, and then sine square alpha. Note that in the expression we have alpha, so that means this secondary maxima intensity is a function of theta as well, because alpha is k by 2 multiplied by a and sines of theta. That means the secondary maxima will have the effect. It will not be same for all the cases. There will be some change, some variation, but this variation is small, so eventually it looks like a same peak. Well, now further we try to understand the spectra, because the total intensity pattern not only contain this term, then the diffraction term is also there. So, that means sin square beta divided by beta square and sin square n alpha divided by sin square alpha. So, this term is also there, which I write in the bracket. So, the total intensity of the total intensity will be the multiplication of these two, and if I do that, we know that there will be a envelope that is generated by. So, it should be something like this. So, let me draw it here. So, okay, maybe in the next page, because this is a big picture. So, let us use the next. So, we have the spectral distribution for this is the distribution for this function. And this is the change, say alpha or theta, whatever. Now, on top of that, if I put the spectra, the intensity of the diffraction pattern, then it should be like this. So, this dotted line corresponds to sin square beta divided by beta square. So, how the overall spectra will look like? So, it seems we have this something like this, an overall spectra one can expect, which is a combination of these two. So, I plot here I, that should be a function of theta with this form, and this is the combination of this. So, here also there is a possibility, like here in this case, the maxima of one spectra, one is coinciding the minima of another. So, that means there is a possibility that we can have something called absent spectra or missing spectra, absent spectral line. What is absent spectra? Suppose pth order principal maxima For interference, that is for interference, that is for this term, that one can find when we have alpha equal to p pi, and then we get a sin theta is equal to p lambda. That is the condition for principal maxima, and alpha, when alpha, let me write, it is k by 2 a sin theta. Several time I wrote this, by that time you should familiar with this notation. It is pi by lambda a sin theta, and beta is k by 2 b sin theta, which is pi by lambda b sin theta. These two we know, and then from the condition for principal maxima we can have this. Now for the same theta, what we have, if we have the mth order diffraction minima, that is coming for the term sin square beta divided by beta square. From that term one can get this. Then we have another expression for the same theta, and we have here I can write, then beta is equal to, actually I am looking for the minima, this is m pi, where m is not equal to 0. That is the condition of the minima of this. So that means we have b sin theta, same sin theta, we have m lambda. So we have one equation, let us put this equation 1 and this is equation 2. So we have equation 1 and equation 2, and they should be same, they should be for same theta. So I can write from equation 1 and 2, we have sin theta is equal to p by lambda a, that is equal to m lambda by b. Again we have a relationship between a and b, so that means a by b is p by m, the ratio of two integers. So that is the condition of missing order. Like we have for double slit, exactly the same thing. This is the condition for missing order. That means when A is this, let me draw what is A. So A is this and this is B. When A is for example 2 of B, then this ratio, so when suppose A is to B, then A by B ratio is 2. So, we have P by M equal to this. So, P is the order for maxima. So, P will be 2 of M. That means when M is equal to 1, 2, 3, etc., then P will be, so when M is equal to 1, 2, 3, etc., P will be 2, 4, 6, etc., and this will be the missing order for for coming, that should come through interference pattern for interference. For interference. So, like in the exactly like for double slit, for multi slit also we can have these spectra, that is we call the missing order. The next thing that we need to understand regarding the grating spectra is something called angular dispersive power. Angular dispersive power of grating. So, angular dispersive power means how we can separate with respect to wavelength, how the separation is there. So, let me first define and then let me quickly. So, this is the quantity we want to find, dispersive power. So, what is the meaning of that? So, we know that this is the spectra for grating. So, let me draw the spectra for one given wavelength. So, we have a maxima here, and then we have secondary minima, and then a maxima here, and then secondary maxima, then maxima here, and this is for a given wavelength. Now, if I have another wavelength, and for that wavelength if I like to draw the same curve here, there will be a slight shift of the same theta, because the condition for maxima we know, and that condition is A sin theta is equal to m lambda. So, for different lambda for a given theta, the condition will be the emit order will change. So, maybe for other wavelength we have a spectra something like this. So, that means there is a shift of this principal maxima, whatever the maxima we have, there is a shift, and that shift is expected because I am dealing with another wavelength. So, order, and both the wavelength are they are obeying this equation. So, there will be a shift. Now, if there is a shift, then what happened? So, with the same theta there will be a separation. So, how much separation with unit lambda one can have, angular separation, and that basically measures the dispersive power of a grating. So, the rate of change of the angle of diffraction that means I am talking about the theta with wavelength lambda. How with wavelength lambda there is a shift of theta in order to get the same order of principal maxima. So, we have I is equal to I naught sin square beta divided by beta square multiplied by sin square n alpha divided by sin square alpha. That was the form we have. Now, for pth order principal maxima, we have A sin theta is equal to P lambda, that we already mentioned here, that is the condition we have. So, here I can write A of cos theta then d theta d lambda is equal to P, or in other word d theta d lambda is equal to P by A sin theta. So, that means d theta d lambda that is proportional to 1 by A for a given P and theta. So, 1 by A means, what is 1 by A? 1 by A is essentially number of ruling per length. Typically, the grating has a ruling per millimeter, few hundreds or few thousands. So, if the number is high, then the resolving power of the grating should also be high. So, angular dispersive power of the grating increases with increasing number of ruling per unit length. So, if the number of ruling is very high, then that basically increases the dispersive power of the system. So, with that note, I do not have the time to discuss more about the grating spectra or other property of the spectra. So, I would like to conclude here today because of the lack of the time. So, in the next class, we start from here and try to understand another quantity which is called the resolving power of the grating. So, with that note, I would like to close my topic here. I like to stop my discussion here. So, see you in the next class, and thank you for your attention.